This is a video over titration problems. Before we begin looking at what titrations are, we're going to look at what a neutralization reaction is. So getting to the second slide here, if you remember, a neutralization reaction occurs between what is a strong acid and a strong base. So a strong acid and a strong base are going to be a part of a neutralization reaction. When you combine these two, strong acid, strong base, in solution, you're going to get a salt. And remember that the salt is a metal plus a non-metal. Okay, and you're going to get some water in the form of a liquid. So we also talked about in a neutralization reaction, we talked about hydronium ions and hydroxide ions, those H3O plus ions and those OH minus ions, they are equal to each other in a neutralization reaction as well. So the pH would be a 7 or neutral. Looking at types of neutralization reactions, I'm going to show you how salts that are produced from these reactions can be neutral, they can be acidic, or they can be basic. So taking a look at these three examples here, let's see. The first example we have is between a strong acid and a strong base. So here hydrochloric acid is a strong acid, sodium hydroxide is a strong base, and through that reaction we get a neutral salt and we get water in the liquid form. So that salt is dissolved into the water and we produce a neutral salt from a strong acid strong base solution or reaction. And then the second equation here, we have what's a weak acid, acetic acid plus a strong base. So a weak acid plus a strong base is going to give me, again, it's going to give me a salt and it's going to give me water, right, in the form of a liquid. But what we notice here is that in the case of the weak acid becomes my salt, which becomes my conjugate base, right? So in this case, the salt is going to be basic, right? The production of that salt is a basic salt because it was a weak acid, now becomes a conjugate base. So basic salt. In the next reaction, we have a strong acid plus we have a weak base. And in this strong acid, this weak base, we're going to get again a salt that is produced. Let me rewrite that. A salt that's produced, and then we're going to get some water in the form of a liquid. But here we'll notice that this weak base now becomes my conjugate acid here, and in this case here, the salt that was produced is going to be rather acidic. Okay, I'm not going to get into too much more detail about that, but I'm just going to kind of leave it there. And these three reactions are just kind of a basis of why some salts are neutral, why some salts are basic, and why some salts are acidic through the reactions. So now we can get into titrations. What's important here in titrations is that we're looking at acids and base reactions. That's what we're looking at. And in a titration, we're going to know the molar concentration of either the acid or the base. We're going to know the volume of both the acid and the base, and we're going to use that molar volume of the acid and the base to determine an unknown. So usually the unknown will be the molarity, but in some cases you might be looking for the volume. So things to know about a titration. Titration is a reaction between an acid and a base, and in a titration we usually have what's called a standard solution. And in a standard solution, by definition, it's the solution that we know the concentration for. So again, this standard solution can be an acid or it can be a base. So it can be an acid or it can be a base, and we're going to know the concentration, in other words, the moles per liter, that molar volume, and we're going to know the volume of it, and we're going to compare that to an unknown. Sometimes it might be the molar concentration that we're looking for, and we'll know the volume of the unknown. And it might be reversed. We may know the molar concentration of the unknown, and we're looking for the volume. Sorry, I should have put a question mark there. We might be looking for the volume there. So that's what we're gonna do through this titration. Okay, so again, a couple of things that are important here is knowing the standard solution. The concentration of the standard solution is known, and we're going to be using that standard solution to place it into an unknown solution to determine its concentration. Two more things that we need to know for titrations are, one, the equivalency point, and the equivalency point is where the hydronium and hydroxide ions are equal to one another. So once these two concentrations, molar concentrations, are equal, then we know that we've reached the equivalency point. And how do we determine that? Well, we have to have something that we can look at to determine the equivalency point between these two ions, and that's what's referred to as the endpoint. The endpoint has some kind of an acid-base indicator that's going to change in color, right? And that'll, hey, you've reached the equivalency of the hydronium hydroxide ions, okay? And that indicator is placed into the unknown solution. So up here, whatever's in this beaker is usually the concentration that we don't know. So we usually know the volume, but we don't know the concentration. And what's in this apparatus up here on top, that we know the volume and that we know the concentration of. So we know both of these, and we can solve for one or the other for what's in that beaker. So what's in this apparatus up here on top is also what we referred to in the last slide as the standard solution, right? So that's what's always added into the unknown solution. So what's the equation that we can use to solve for either the molarity or the volume of the unknown? Well, it's this equation here. On the left, you have the acid. On the right, you have the base. So remember that molarity was the number of moles per liter. The volume, you can see it as a milliliter. Sometimes you'll need to change the milliliter into liters. And then the N is the number of hydrogen ions or hydroxide ions that are going to be released by the base or by the acid. So from here, I'm going to work out the last two problems that are in this PowerPoint presentation. And I'm going to work them out on this Word document here. And the first thing I'm going to do here is I'm going to highlight some of the information that's given to me. So first of all, I know that this first substance is a base because I see the OH there, that hydroxide. They are giving me the molar concentration and they are giving me the volume of the base. From there, they're giving me the volume of the acid. How do I know that this is an acid? Well, it starts with a hydrogen, and they're giving me its volume, and they want to know what the molar concentration of that acid is going to be. So here, the base is my standard solution, and the acid is my unknown. So I'm looking for the concentration of the acid. So I'm going to write the equation that we saw before. So that's the concentration of the acid, the volume of the acid, the number of particles or the number of hydrogen ions that are going to be given off by the acid is equal to the concentration of the base times the volume of the base times the number of particles or hydroxide ions that are given off by the base. So here I'm going to write these down. The concentration of the acid is what we don't know. We know that its volume is 50.0 milliliters. And I'm going to look at how many hydrogens I have here. I have 2 hydrogen ions that are going to be given by that acid. So here I'm going to put 2 because there's a 2 behind the H. Then I'm going to do the same thing with the base. I'm going to write down MB. It's not perfect. It's kind of a little bit of issues there. MB. I'm going to write VB and NB. Whoa, that went real off base right there. So they give me the concentration of the base at 1.3 molarity for the potassium hydroxide. For the volume of the base, they give me 42.5 milliliters. and I look at the number of hydroxide ions that are in that base, and it's 1. So now here I'm just going to simply plug it into the equation, and so I get x times 50. I wrote the wrong number. X times 50 times 2 is equal to 1.3 times 42.5 times 1. So simplifying this equation, I get 100 times x is equal to 55. The next step would be to divide both sides by 100, and I get x is equal to 0.55, and that's going to be the molar concentration of the acid. Let's see if this thing catches up with me. So here, from the standard solution of the base, we added this much volume of the base, had that concentration into that volume of the acid, and I used that to determine its molarity at 0.55 moles per liter for the acid. So that's problem number 1. Problem number 2, let's see what they're giving us. We read through the problem, they're giving me 15 milliliters of a base. They're also giving me its concentration of 0.215. They are giving me an acid, and they're giving me its concentration at 0.645. So we already know the concentration of the acid here. They are asking us, let me get rid of that message. They are asking us here for the volume of the hydrochloric acid. So how much acid was in that beaker that we were adding the base to? So let's take a look at rewriting the equation like we saw before. Not perfect, but close enough. So in this case, let's write down what they've given us. They gave me the concentration of the acid at 0.645. They give me they didn't give me the volume, excuse me. And then I'm going to look at how many hydrogens are in that acid. Again, I know it's an acid, it starts with an H. There's 1. And I'm going to do the same thing for the base. This time the concentration of the base is 0.215. The volume of the base is going to be 15.5 milliliters. And I look for the number of hydroxides in the base, again, is 1. So setting up this problem, I'm going to get 0.645 times x times 1 is equal to 0.215 times 15.5 times 1. So here I'm going to get 0.645x is equal to 3.33. Divide both sides by 0.645, and I get that x is equal to 5.16 milliliters. Now, sometimes the question might ask me to convert these milliliters into liters. So if I want to convert those milliliters into liters, there's 1,000 milliliters in 1 liter. So dividing through, I get 0.00516. Sorry about that. 516 liters. right? And what are we